Welcome to EPG Pathashala in Computer Science. This is a series of lectures on computer networks. Today we will be looking at quality of service in computer networks. The way quality of service is implemented in networks, what are the techniques that are required for quality of service. So we will start off with the requirements. We will look at the issues that are there in terms of providing quality of service. And we will also take a look at the various techniques that are used. So we will do an overview of the techniques and then we may look at some of these techniques in detail in subsequent lectures. So if you look at network performance and quality of service, so what are the demands that an application normally has from a network? So these are something which are very obvious. Obviously all applications require adequate bandwidth. In fact, they keep asking for more bandwidth. And typically they require less delay, less or no jitter. Remember that jitter is the variation in the delay. There are many applications which cannot tolerate a variance in delay, especially real-time applications. So that is another requirement for an application. And similarly, they would also have to have no loss or minimal loss. So these are normally we say as the performance requirements for a network. So and these requirements you can say kind of determine the quality of service that the network provides. And these requirements vary with the applications. For some applications they require more bandwidth, but they can tolerate delays. Similarly, there are applications which cannot tolerate delays, but they can do with less bandwidth. So similarly with respect to loss and jitter and other things as well. So there are different combinations of these parameters that need to be considered when you are looking at how to provide quality of service for different applications. So if you look at a taxonomy of applications, you can generally classify them in terms of whether they are elastic or real time. So elastic would mean that they can kind of adjust to available bandwidth and available delay and so on. That is, they can tolerate both delays and bandwidth requirements and so on. Real time on the other hand are ones which require they have certain timing constraints or they have certain bandwidth constraints. And real time applications further can be divided into tolerant ones and intolerant ones, which means that a tolerant, for instance if you say loss tolerant, it can tolerate some amount of loss, and there are applications which cannot tolerate at all, so they are intolerant applications. And again under tolerant applications we can look at some applications which are adaptive and then we talk about non-adaptive. So and again we talk about adaptive, it could be in terms of whether it is delay adaptive or rate adaptive, so which is it that it can adapt to. Okay. So there is actually you can see a class of different types of applications, and each of these require different qualities of service. Their requirements from the network are different. Okay. So why do we have to worry about this quality of service? Okay. So let us look at what is the current scenario in our IPv4 networks. So in IPv4 networks it only provides you a best effort service. Since it provides only a best effort service, there is no direct support for quality of service in IPv4. Okay. But you cannot replace this network with another network because the internet architecture, the Ethernet IP combination has become very popular and is widely used. Okay. And we also see that the QoS required for many applications varies. For instance, as we said, some of them require guaranteed service, some of them can adapt to the situation. And some of them have these bounds in terms of the delay and they have fixed sending rate requirements, and some of them can tolerate these delays and other things. Okay. So given that the network is only providing a best effort service, but there are applications which require this kind of quality of service, how do you ensure that? How do you ensure this kind of a quality of service in a best effort network? That becomes the main question. So what is it that we have to do? We have to take some specific measures and we have to come up with some specific protocols in order to support QoS over this IPv4 network. Okay. What we also have to do is we have to make use of the resources very effectively, right. So you have to allocate the resources effectively and you have to use them effectively. So to do this there are a number of techniques that have been put forth. So we talk about techniques like admission control, classification, scheduling, policing and so on, different protocols that have been developed in order to support these kind of functions. So when you talk of admission control, we are talking about whether we will allow a connection to be established. Remember that IPv4 is a connectionless network, but do I allow a particular application to be permitted into the network to start sending packets to the network? Can I control it depending on the available bandwidth and depending on what its requirement is. Okay, that would be that is what those are kind of things that we would like to see under admission control. Similarly, do I have to classify traffic? So do I just look at packets, because basically it's just a packet by packet forwarding, but can I classify the packets and provide better service for certain types of packets and so on? Okay, how do I schedule them? Remember that we have different buffers. There are packets coming and sitting in various buffers, and we have to pick them up from various buffers and send it out onto the lines. So can I bring in some effective scheduling mechanisms over there in order to support different qualities of service? Okay, do I have to do some policing? Somebody says they will send data at a particular rate, but they send it at a different rate. So do I need to have some kind of a traffic policing? So these are all different techniques that people have put forth with respect to providing quality of service in an IPv4 network. This is what we will be looking at now. Okay. And the diffserv, intserv, RSVP are all different protocols that have been designed in order to support these kind of requirements. Okay. So when we talk of the resource allocation in a network, what exactly are the resources? Basically two, right? One is the bandwidth of the links, and second is the buffers that you have at the routers and switches. Okay. And typically what happens is that packets content at a router for the use of a link, and what happens when each packet comes in, it is placed in a queue. If there is already something that is being transmitted, it goes and sits in a queue. Okay. So when too many packets are contending for the same link, what happens is the queue keeps getting filled up, and if it gets filled up and a packet comes in, the queue will overflow and a packet will have to be dropped. Right? So that will lead to loss of data, loss of packets. So we are talking about use of these resources in such a manner. So what we actually have to do is use these in such a manner that packets do not get dropped, that the queue does not become full, and you are able to support many applications. So that becomes our basic problem. So but let us look at what are the issues that we have in this resource allocation. Now given that we are talking about a packet switch network as an IPv4, which consists of multiple links and switches, right, and routers. Now, the moment we say multiple links and switches, the capacity of each of these links varies. Okay. So, for instance, you could have more than enough capacity on the immediate outgoing link, right, but somewhere in the middle of the network, you may not have enough resources. Take this example for instance. So, let us say I have these edge nodes are connected by means of 100 megabit per second to a switch here. Now this switch is connected to a destination or to another router, let us say, using a 1.5 megabit per second link. So now what happens here? Here I have enough bandwidth, but this router now, since it can send data out only at 1.5 Mbps while receiving data at 100 Mbps, will become the bottleneck. Naturally you can see this is output is slow, therefore packets will start queuing up at this router. Okay. So this obviously is our major problem. So second thing we have to look at is when we are looking at data flowing through the network, basically we look at them as packets, but we can also identify what are called as flows. Okay. So what do we mean by a flow? Flow essentially is a set of packets which can be said to belonging to a particular set of endpoints. Okay. So for instance, you could have flows defined at various granularities. You could say host to host can be considered as a flow, or you can say packets going from a particular process to another process can be considered as a flow, and so on. Okay. So if you can identify packets as belonging to flows, the advantage that we will get is that if you have taken a decision for one of the packets, you can use the same decision for the rest of the packets, and you can make the processing faster. Okay. So which means that we need to identify and classify flows. And once you have done this classification, you will also be able to give differential or preferential services to certain flows over the other. Okay. Of course, this will require that some kind of soft state will have to be maintained. Remember, one of our advantages of the IPv4 packet switching mechanism is that it does not require any state to be maintained at all. But whereas when we bring in flows, there may be some amount of state that needs to be maintained, maybe some kind of a soft state. Okay. That is another challenge that needs to be looked at. Another fact that we need to keep in mind when you are looking at resource allocation is with respect to the evaluation criteria. Now, how do we normally evaluate whether my resource allocation is getting done properly or not? There are two principal metrics of networking, right? One is throughput and the other is delay. So you can always look for whether your throughput is good and your delay is minimal. But the problem often is that these two are kind of contradicting goals. They are conflicting goals. So what is normally done is that a new metric which is a combination of these two is also used. So it's called as the power of a network, which is defined as throughput divided by delay. So if you look at plotting the load versus the throughput by delay or the power of the network, you will find that you need to find a point. Okay, if you will find that as the load increases, the throughput is likely to increase up to a particular point, and then you will find that as the load increases, throughput divided by delay starts decreasing. Now, if you look at this throughput divided by delay, you can see that we are trying to capture the fact that throughput should increase and delay should decrease, and when throughput increases and delay decreases, your power will be higher. So that is what we are looking at. So you will find that this typically happens to be the nature of this throughput by over delay when the load increases. So what we actually need to find is, we need to find this optimal load point. Okay, if you are operating around this point, you will find that we are able to support many different applications with the quality of service that they need. Okay, that's one of the criteria that we need. So this gives us some kind of a guidance in terms of what to look for. Okay. There's another challenge also when we talk about resource allocation, which is the fairness of the resource allocation. Again, that becomes another evaluation criteria. So basically, you would like all flows to receive equal share of bandwidth. So what are the challenges that we have here? One of the major challenges is that when we use some kind of a resource reservation, right, especially when you want to provide preferential treatment to certain packets, automatically that itself creates some kind of an unfairness, right. So any reservation based resource allocation mechanism will create some unfairness. So if you, for instance, let's say we have a video stream, may receive a 1 megabit per second data rate across some link, while a file transfer receives only 10 kilobit per second. Okay, so you can see that they are not receiving equal amount of the bandwidth. Okay. Now there are further challenges. See, if you take, for instance, different flows, let's take this example that's given here. So I have a flow here which is going through multiple routers. We're going through 4 routers. Okay, so it's a 4-hop flow. Okay. In addition to that, there are also some single hop flows which are kind of there at each of these links. So you actually have this 4-hop flow contending with 3 different 1-hop flows. Okay, so this fellow is kind of at a major disadvantage because he needs to be fighting with many more people at every stage. Okay, so but how do we handle these kind of situations, right? How do you capture this? How do you handle this? These are all very interesting challenges that we have in terms of how effectively resource allocation can be done. So if you look at some of the solutions that have been proposed for solving all these problems, you will find that there are 2 types of solutions, right? You can either have a network-centric solution or a host-centric solution. Now remember that most of this problem occurs at the network. So ideally we would like to have a network-centric solution, which means we would like some things to be done at the routers inside the network. Okay, do something inside the network, let the routers do something in order to provide the quality of service, in order to do the resource allocation effectively. Or it could be a host-centric mechanism where the host will kind of try to guess or try to estimate what is happening in the network, and accordingly they will have to implement certain measures. Another option that we have is a reservation based or a feedback based approach. Now normally you can see that the reservation based approach will go with a network centric approach, and a feedback based approach will go normally with a host centric approach. That is, in a reservation based approach, what you do is you reserve for resources before you actually start sending the data or start using it for the applications. In a feedback based approach, no reservations are done, so you just go ahead and start sending data into the network. And as the network gets congested or as the performance varies, based on a feedback, either in terms of the delays that you experience or whatever, you initiate certain measures. Okay, so you will normally find that therefore feedback based mechanisms are more tied up with the host centric ones, and reservation based are more suitable for the network centric ones. And in terms of how exactly the allocation is done can also be divided in 2 ways. One is a window based allocation and a rate based allocation. So in window based allocation, what we are essentially doing is we give advertisements and window advertisements, okay, in order to reserve the buffer space. So when you talk of window based, we are talking about specifying in terms of the amount of data or amount of buffer space that you want to give. Then in case of rate based, we are looking at controlling the sender's behavior using a rate, that is in terms of how many bits per second the receiver or the network will be able to handle. Okay, so in terms of that, you can control the allocation of the resources. Okay, so you'll find that these are certain common techniques, right, which fall under one or more of these categories that are normally used. Okay, so now let's come to typically the kind of solutions or the actual techniques that are employed in order to provide this quality of service and in order to do the resource allocation effectively. Okay. Now, the first thing is, one of the easiest solutions that you can think of would be that you just deploy enough link capacity so that congestion does not occur. Okay. So, increase and provision enough amount of resources in your network so that the traffic flows without any delay or loss. Okay. So, obviously, it is a very nice solution, very low complexity because nothing much has to be done in terms of the network protocols or in terms of the resources inside the network, but obviously the costs are very high, right. You need to spend lot more in terms of getting high bandwidth networks. That is there. Plus, there are certain challenges in this network dimensioning as well. So, when you say enough link capacity, how much exactly is that enough capacity? How much bandwidth can we say is enough? As you can see, if you look at the different applications that have been developed, we find that as more and more capacity is given, network capacity is given, applications start demanding more and more from that. So, it is a kind of what do you say, it is a cyclic process where one is driving the other. Okay. Your applications become better because you have better capacity, and once the capacity increases, applications start demanding much more from the network as well. Okay. So, there is a challenge there. Okay. And how do I estimate the network traffic demand? Okay. Because I need to estimate it, only then I will be able to say whether the bandwidth is enough or not, okay, for that much traffic. But what we actually have so far is only a best effort service. So, what do we do? So, we have this one size fits all model that obviously is not going to be useful. So, first thing that we need to do, start looking at, will be to look at having multiple classes of service. So, you partition the traffic that is coming into classes. So, it is one of the first approaches that we have to do, first practical approach that we can look at. So, what we are talking about here is that network will start treating different classes of traffic differently. Once it does that, then it will be able to give preferential treatment. Just as, you know, for instance, you have a VIP service versus a regular service in many places. So, a VIP service obviously will get better treatment, right. So, similarly, you can have VIP traffic which will get faster treatment or better treatment. That is one thing. Second thing is the granularity at which this differential service is to be provided will have to be decided. Agreed that we have to put it into classes, but at what granularity? That's an important task. So you would typically like to do it for classes or flows rather than giving it for individual connections. So that's another reason why we would definitely have some kind of a classification, or we would desire some kind of a classification. Okay. For instance, we actually have support for this even in the IPv4 by means of the type of service bits that are available. So you could use the type of service bits, for instance, to classify or to group different flows into classes and use that information for providing different types of service. So for instance, I could have a 1.5 megabit per second link here, which is used by two different endpoints or two different flows, so to say, right? And I would like to have different treatment for both these flows. Okay. For instance, one of these flows could be a HTTP traffic and one could be a voice over IP traffic, right? So what could happen? Okay, so let's say we have 1 megabit per second voice over IP, and I also have a HTTP. Both of them are sharing a 1.5 megabit per second link. Now, normally you don't expect HTTP to really interfere with the VoIP traffic, but sometimes what can happen is that a burst of packets can come from because of HTTP. So HTTP burst can come and congest the router, and when it congests the router, it can cause the audio packets to be lost. Okay, so now what would we like to do normally in such a situation? We would like to give priority to audio over HTTP because we do not want audio packets to be lost. Okay, so that is one of the challenges that we have. So how do you make this happen? Okay, so one of the things we need to do for this is that we need to have some kind of a packet marking scheme. Okay, in order to identify that these packets belong to a particular class and the other packets belong to some other class. Okay, so we need a packet marking at the routers to distinguish between different classes, and a new router policy to treat packets accordingly. Okay. So far routers have been treating all packets similarly, right, but we need to treat different packets differently. So that mechanism has to be provided. That is the first principle that we need to think of when we talk about providing QoS guarantees. Okay. Now, even in this situation, there is a possibility that applications can misbehave. So which means, let's say I have the VoIP traffic that we talked about. Okay, it was supposed to transfer at 1 Mbps, but what if it sends data at a rate which is higher than 1 Mbps? It is declared that it will send data at 1 Mbps, based on which you have provisioned some bandwidth. What if it violates that and transmits much more data? Okay. So obviously this means we will have to be careful about it. We need to identify that, right? So we need to have some kind of a policing mechanism so that you can force the source, you can identify and force the source to adhere to the bandwidth allocations. So that is another important aspect. So we need marking and policing at the network edge so that at the core router, when it is getting, the packets are getting checked, they can be sent appropriately. Okay. So at the edge, you can see that I need to do some kind of packet marking and packet policing so that I am able to regulate the flow of data, I am able to identify the different flows of data. So second principle that we need to look at therefore is you need to protect one class or isolate one class from the other classes. So that is another thing that needs to be done. So if you look at different policing mechanisms that are normally used, okay, what is it that we want to do? We just want to limit traffic to not exceed the declared parameters. So there are many criteria that can be used in order to identify whether it is violating its declared parameters or not. Okay. So one is you could look at it in terms of average rate over a long term. How many packets can be sent per unit time in the long run? Okay. This is one parameter that could be considered. But the crucial question that comes here is what is the interval length? Okay. For instance, when you say how many packets can be sent per unit time, so if you say for instance 100 packets per second and 6,000 packets per minute, okay, you will find that both will have about the same average. So what is the time duration, right, over which, or the time interval over which we are looking at this amount of average rate that is to be done? Okay, that's another important question there. Similarly, we can talk about peak rate. Okay, so peak rate is that this is an important parameter because though on an average it may be sending data at a particular rate. For instance, we may have 6,000 packets per minute, but it may suddenly send data, bursts of data at a higher rate. So for instance, you could have 1,500 packets per second peak rate, but have a 6,000 packets per minute average rate. So this is also something that needs to be considered. And of course, we talk about burst size. That is, when you say that you can get bursts of data. What do you mean by burst of data? It's the number of packets or a maximum number of packets which are sent consecutively without any intervening idle time. So which are coming kind of together. Okay, so these bursts are the ones which can always cause congestion to occur. Okay, so this is so we need to look for these and we need to control what can be the maximum burst size, what can be the maximum peak rate, what can be the average rate and so on. So if you control these parameters, you can do some kind of a policing mechanism. Okay, so that is one thing. So next thing that we also have to look at is when you are allocating this fixed bandwidth, okay, to different flows, if you have an inefficient use of bandwidth, then that also can be a problem. So which means we need to have mechanisms to efficiently share the bandwidth. Okay, so for instance, if you have this 1 megabit per second VoIP sharing data with another, let's say some HTTP traffic, okay. So now you may want to provide 1 Mbps for this logical link and 0.5 Mbps for this logical link. Okay, so how do I, so if I do that, then are my resources being effectively used? Okay, are they being shared efficiently? So this is another important aspect to look at. So while you provide the isolation, you would also like to use the resources as efficiently as possible. That is, you don't want to reserve some resources for a particular flow which is actually not used by it. Then you will find it's not being used very effectively. So that also has to be considered. So normally what we do for ensuring this is that we have different scheduling mechanisms. So the scheduling mechanisms kind of make sure that you are able to use the network resources effectively. So if there is some unused resource, you would like to use that resource. So this scheduling problem basically is that of determining which is the next packet that needs to be sent out on a link. Okay. There are different techniques that are used for this, some very commonly known techniques as well. So as we talk about normal scheduling, right, even in the context of OS and so on, we talk about scheduling. So similar scheduling techniques are used here also, but with some variations to handle the network related issues. So you talk about first in first out can be one scheduling technique, just send data in the order of their arrival to the queue. Or you could have a round robin kind of a technique or a fair queuing kind of a scheduling. So in round robin you will have data sent from multiple queues, okay, different flows may be classified into multiple queues and you pick up data from the different flows and send them out. Okay. And you can also have priority based and you can have weighted fair queuing and so on. Okay. There are different scheduling mechanisms that can be considered. Okay. So when you talk about scheduling, we also talk about the discard policy, which is what happens when the packet arrives to a full queue. You know, which packet do we discard? Do I drop the packet just arriving, which is called as a tail drop mechanism, or do I do it on some priority basis, a drop or remove based on some priority class, okay, or at random. Okay. So there are different mechanisms that are used here as well. So that also has to be considered. Okay. And another fact that needs to be also looked at is, basically we need to understand that you cannot support traffic demands beyond the link capacity, right. So if I have a 1.5 Mbps link and I have two different flows both requiring 1 Mbps capacity, obviously you will not be able to support it, right. So what do I do in this case? It would be good if I can have some kind of a call admission procedure. That is, a flow will declare that it needs so much, right, and the network may either block the call if it does not have so much of resources to give, or it may allow it to proceed. Okay. So if it cannot meet the needs, it can at least inform that application that you will not get this much of resource. Okay. So we need to have some kind of call admission techniques as well. Okay. So this gives us the different QoS techniques that we need to consider. So we need to have classification, we need to have traffic shaping and policing, and we need to have scheduling, and we need to have call admission control. In addition to this, we will also require something like signaling, right. So in order to, when you talk of call admission control, you may have to signal that you want to reserve resources or you want so much resources to the network. So you need some signaling mechanisms, and I will also require some QoS aware routing based on these things effectively. Okay. So if you look at these 6, you will see that these 3, the signaling protocol, QoS routing and admission control, they will come under the control plane, and classification, policing and scheduling will come under the data plane. Okay. So, okay, so it's just an example of admission control. So if you look at this, for instance, I have this, let's say my maximum bandwidth that can be supported is 10 Mbps. This is my current bandwidth. So I have a path which requires 3 Mbps. So an application makes this requirement. So I need to make sure that I am able to support the 3 Mbps bandwidth given that I have so much. So if you look at the objectives and issues of admission control, you will find that you need to provide a mechanism to admit users' resource request according to the current resource usage and the user's requirement. So this is important. Okay. So major issues that we get here are, so how do you get information about the link resource usage efficiently, and how do you make sure that you are not doing overbooking, that is you are not providing more resource than what is actually required. Okay, those are interesting things. So there are many approaches that are used here. We have statistical based approaches which are which apply specific traffic models which know what kind of traffic is coming, and they know these specific traffic models, and they apply these traffic models, okay, in order to do the admission control. But the difficulty here is it is it is kind of not so accurate and to give a very tight traffic model. Okay. So in which case you may end up with some low utilization of the network, because you might have planned for worst case scenarios. So in which case you may end up doing you may end up having very low utilization of the network. Okay. Another approach that is normally used for admission control is measurement based, because I need to know how much of bandwidth is currently being used, right. So what is normally done here is that you kind of take an exponential average over consecutive measurement estimations. So the normal weighted average mechanism that is used, weight the original older value by a factor of 1 minus W, and W for the current measurement, and calculate the new measurement and make your estimations based on this measured values, or it could be based on some time windows and so on. So these are certain techniques that are used for admission control. This again cannot be used to provide very tight guarantee constraints, and measurement is expensive. So that's a challenge in this kind of an approach. Okay. And if you look at flow identification, so the objectives for flow identification basically is that you need to identify a packet as belonging to one flow or the other, and the packets and the fields that can be used for the flow identification vary from source IP, source port number, destination IP, destination port number, protocol ID and so on. But the issues that come here are how fast are you able to do this classification. Okay. The search speed becomes important, low storage requirement, fast update, scalability, these are all issues that come up over here. Okay. So how do I actually search, right? Do I do a direct memory lookup, or do I do a binary search? So you normally have the usual space versus speed trade-off that you need to be looking at. So those are issues that one has to understand in terms of how flow identification is done. And this is a general mode of queuing disciplines. We will be looking at queuing disciplines in much more detail in a subsequent lecture. So it could be a single FIFO queue or multiple queues and so on. So these are other things that one needs to look at. Okay. Another very important aspect is our traffic regulation and traffic policy. That is confirming the incoming traffic for each flow to its traffic specification. So a very common technique that is used here is what is called as a token bucket algorithm. So what is normally done here is that you define, you kind of have something like a bucket, and with a depth of V, and you define an average rate of R. Okay. So a token bucket typically generates tokens at the rate R, okay, and keeps accumulating it in the bucket. So when packets come in, when incoming packets come in, okay, so they can they are queued and they are sent out from the queue to the output queue only if there are tokens available. So depending on the availability of tokens, you can send out the packets. So if you have accumulated tokens by not sending packets earlier, you can send a burst of packets. Okay. So you this token bucket mechanism kind of allows for sending burst of packets, provided you have not used that, provided you maintain your average rate within the actual stated limit. Okay. So this is one of the algorithms that is used for this purpose. Okay. So you limit the input to the specified burst size and average rate. That is the goal of the token bucket algorithm. So if you look at how this is implemented, so what we do is you have this bucket which can hold B tokens, and tokens are generated at a rate of R. Okay. If the bucket is full, obviously you cannot put more tokens into it, it will be discarded. So over an interval of length T, number of packets that are admitted will be less than or equal to RT plus B, right. R into T is the rate at which the tokens are generated into the time, plus B refers to how much of tokens have been accumulated in the buffer. Okay. So that much amount of packets can be sent out. So if you look at this example, so let us say R is equal to 1, okay, you are generating 1 token per second, and I have a bucket of capacity 10. Okay. So if I have packets coming in here, let us say at T equal to 10 seconds, right, I have 10, nothing has been sent, so 10 packets, 10 tokens have been accumulated in the buffer. Now at T equal to 15 seconds, so when this packet 10 comes in here, there are 10 tokens available in the buffer, so this 10th packet with size 10 can now be sent out. Okay, I send this out. Now at T equal to 15 seconds, nothing else has been sent, so 5 more tokens have accumulated here, okay, but I need to send a packet of length 9, so I need to have at least 9 tokens before I can send it out. So what will happen now? At T equal to 19 seconds, you will find that you would have got the 9 tokens that are required, so you can send out this packet of size 9, okay, and this packet 5 of size 5 will be waiting. At T equal to 24, we will see that this packet can also be sent out. Okay. So once that you can see that the bucket kind of fills up and empties once the packets have been sent out. So you can kind of regulate the flow at the rate at which the data is sent out using this mechanism. With respect to packet scheduling, again there are multiple issues. We will look at packet scheduling also in detail subsequently. Okay. And packet discard, this is also another thing that we talked about, right? Whether you do a tail drop or you do an early drop with respect to discard management, that is also another important aspect. So these are also issues that need to be considered. So overall, if you look at a QoS guarantee scenario, you can see that all these different mechanisms have to be used together. Okay. So you need to have QoS sensitive scheduling, right, at the routers, right. You also need to have resource reservation that needs to be done, call setup, signaling and so on, traffic and QoS declaration, per element admission control. So if you put all these things together, we find that even in an IPv4 network, you are able to provide good QoS guarantees. So that is basically what is happening in today's network. So we will look at more details of these things in subsequent lectures. To summarize, what we have looked at in today's lecture is the various issues for supporting QoS in the IPv4 network and the various techniques, an overview of the various techniques that are used for that purpose. Thank you.